Lesson 8-2, Interpreting Graphs of Exponential Functions. Some key features of exponential functions. So when you have an exponential growth or an exponential decay, the form is still the same, a times b to the x power. The difference is where your b is. If b again is greater than 1, then it's a growth. If b is less than 1 but greater than 0, it would be a decay. Now the domain and range. The domain and range is going to be the same for both growth and the decay. The domain is always going to be all real numbers, and the range has to be greater than 0 because your asymptote is going to be at when y is 0, so it has to be above where y is 0 or the x-axis. When you're talking about the intercepts, they're both going to have only one y-intercept because it crosses the y-axis once, but it never crosses the x-axis, because if it crosses the x-axis, that means y is 0, and y will never equal 0 when you have an exponential function. The end behavior for a growth, as x increases, your y increases, but as x decreases, it approaches 0. And then for a decay, as x increases, y approaches 0, and as x decreases, your y increases. When we say that it approaches 0, that's just another way of saying that it doesn't touch 0. First example, each time you fold a piece of paper in half, it doubles in thickness. If a piece of paper is 0.05 millimeters thick, then you can determine the thickness y of a piece of paper given the number of folds, x, with the function y equals 0.05 times 2 raised to the x power. Analyze and graph the function, then find and interpret the key features, including any constraints on the domain in the context of the situation. So the first thing is determine whether the function represents an exponential growth or exponential decay. Now our base here determines if it's a growth or a decay. Since our base is 2 and that's greater than 1, we know that it's an exponential growth. So that means our graph is going to go up from left to right. So it's going to look something like this. Here the graph is already created for us, but you can see how they created the graph. They have our function right here, y equals 0.05 times 2 to the x power, and they chose some x variables. They chose both some negatives and positives. I would recommend using smallest numbers possible. So -2, -1, 0, 1, and 2 would be pretty good to use. The more you do, the more accurate of a line you're going to have, but there is not a set number you have to have. I would say, I guess the minimum I would do is 3, but you should have enough where 0 is one of the x coordinates, because that's going to be where it crosses the y-axis. So here you can see if you put -2 in there, you get 0.0125, and then it gradually gets bigger as it goes down to x equaling 4. So they plotted them here. You can see the points on here, and it gradually gets bigger, and then all of a sudden it jumps up rapidly. So now from that, we're going to describe the key features. These are the key features we're going to look at. So the intercepts, it only has one intercept, which is the y, and our y is right here. So if I go back to my table, y-intercept would be 0.05. So this would be 0.05, and then to be specific, let me put it as 0 and 0.05. And what does that mean? That means that the thickness of the paper before it's been folded is 0.05. So this is the thickness before the fold. Increasing and decreasing. Well, this one for an exponential growth, this is always increasing. And you always read from left to right. So from left to right, it's always increasing. Positive, negative, it's always above the x-axis. So this is always positive. The domain We said before that the domain is all real numbers. Going back to the increasing and decreasing and positive and negative, why is it always increasing? Because the thickness always increases as you fold it. And then positive, why is it always positive? You can only have a positive number of folds. Or your thickness, the thickness is always going to be a positive number. So let me put that down. I'll just do positive or plus sign. And then the domain is always positive, or to be all real numbers. But for this one particularly, since I can't put any number in there, it can't be indefinitely, so you can't keep going further and further to the right, because there's going to be a point where you can't fold it anymore. So it'll be just restricted to the greatest number of folds. Which just means you're going to fold it until you can't fold anymore because it's too thick to fold. Next would be our range. And our range it has a starting thickness of 0.05. So that means it can't be smaller than 0.05. And I know on our graph here, you see that you could put negatives, but remember your X or your domain is the number of folds. I can't have a negative number of folds. So really you're going to start right here. So our range is going to be y has to be greater than or equal to 0.5. But it can't be infinitely greater than 0.05 because there's a certain point that it's going to get where you can't fold it anymore. So we would say that the relevant range would be restricted. So restricted to the greatest thickness. Of the paper. The asymptote would be when y equals 0, or you can think of the x-axis, which means that the thickness has to be greater than 0. And then the end behavior as x increases, y increases, and as x decreases, y approaches 0. And then the meaning of it, within the relevant domain, the number of folds increases, the thickness of the paper is going to increase. So as folds increase, thickness increases. Next example. The function y equals 3 to the x power can be used to model a real-world situation. The student wants to crowdfund a film project. To spread the word, she shares the page with 3 friends, and the request that each friend share it with 3 more friends. A function that models the number of new people given a link to the crowdfunding page, y, given the number of cycles, x, is defined by the function y equals 3 to the x power. So we are going to determine if this is an exponential growth or an exponential decay. Again, it's all based on our base, and our base is greater than 1, which means this is an exponential growth. Here we have a couple of 4 choices of our graphs, and we have to determine which one would best show that one. Since we know that it's a growth, it has to go up from left to right, so that eliminates C. We know that exponential growths are non-linear, so it can't be B because that one is linear. Now it leaves us with A and B. Now if x is 0, that would make it equal to 1. Now if you notice that A and B, they have different new people or different y ranges or y scales. One is coming by 50s and the other one's coming by 1s. So this one for letter B, it looks a little bit, usually it stays at 0. Remember that could be above the x-axis, but because the range is so, intervals are too big, it looks like there isn't any points above 0 on that one. So another way of looking at this is we could choose some points to determine which one would best fit that. So let's look at here. If we look at 4, where the number of cycles is 4, you can see that in graph A, 4 would be roughly 16 new people. Now, if I look at 4 here, that's going to be roughly there, which would be just under 50, or just under 100, so we could say roughly 75, 80. If I were to put 4 in for x, I would have 3 raised to the 4th power. That would give us 81. So the one that would give us the correct choice of that one would be graph B. Then moving on to part C, list the key features that apply to 3, or y equals 3 to the x power, include the domain, range, y-intercept, and the end behavior of the function, and then determine the relevant range in the context of the situation. So the domain is going to be all real numbers. The range for this one would be y such that y is greater than 0, or you can just say y is greater than 0. The y-intercept, where does it cross the y-axis? When x is 0, it crosses at 1. Then we have the end behavior as x increases, y increases, and as x decreases, y approaches 0. And then we need to determine the relevant range in the context of the situation. So again, if we go back to the original problem, this is talking about friend requests. So if each person shares a page with 3 friends, what would that be? Now you're not going to have x would be, or your x is the number of cycles, so the number of times that it's being shared. You can't have a negative amount. So the first one would be, and you can't have, so the number of cycles would be the number of people that you are, or each person that's going to be sharing it with a group of 3 people. So you have to have a full person, so it's going to be integers, but it'd be positive integers here. So the relevant range for this one would be, you're going to be raising everything to the third, you're actually using cubed. So 3 to the 1st power is or everything would be a cubic numbers. And the reason why it'd be cubic numbers is because if you have a base of 3, 3 to the first power is, or 3 to the 0 power would be 1, 3 to the first power would be 3, and then 3 squared would give us 9, and so on. So we would have our range. So again, this is our x, this is our y. So we would have our range would be 1, 3, 9, and so forth. And it's going to keep getting bigger and bigger. So you're just raising 3 to a certain power, and it has to be a positive number. Another one, for example, 1, a village supply house was down to its last grain of rice. Request of a wise woman. The ruler agreed to double the villagers' rice every day for the next month of September, and the villagers wisely agreed not to use any of the village rice during this time. The function y equals 2 to the x power models the number of grains of rice in the village supply house after x days. Analyze and graph the function, then find and interpret the key features, including any constraints on the domain in the context of the situation. So first we need to determine if this is a growth or a decay. Our base is bigger than 1, so this one is also an exponential growth. Here we're going to graph it. So we'll draw a table of values. And I'm going to choose, let's just choose negative 1, 0, 1, and 2. So if I put a negative 1 in there, 2 to the negative first power would be 1/2. 2 to the 0 power is 1. 2 to the first power is 2. 2 squared is 4, and so forth. So now if I were to graph this, negative 1 and 0.5 would be here. 0 and 1, 1 and 2, 2 and 4. If I did 3, it would be 2 to the third power would be 8, and then 2 to the fourth power would be 16, so way up there. So here's just getting close to the y-axis, but then exponentially growing here. So that's what our graph would look like. Now list the key features to apply to y equals 2 to the x power. So the first thing we're going to do the domain. The domain is going to be all real numbers. And going back to the original problem, it does say that we need to include any constraints on the domain in the context. And x represents the village house supplied after x days. So after x days, so if x is our days, our domain would have to be restricted to positive integers. Or you could just say whole numbers. The range for this one, the range is going to be y such that y has to be, got to be greater than or equal to 1, because you start off with 1 rice. But if you would raise it to, since it's dealing with the month of September, there are 30 days in September. This is going to be less than or equal to, you're going to have 1 million 73 or 1,73,741,824. And how did I get that? If you did y equals 2 to the 30th power, because x would be 30, that would be your last day in there. So going back to my domain, it does have to be a positive. So the restriction would be x such that x has to be greater than or equal to 0, but less than or equal to 30. Because you'd have 0 days in September, and then you'd have 30 days in September. And anything to the 0 power would be 1, so you start off with 1 grain of rice in there. Moving on to the y-intercept. The y-intercept would be 0, 1. It's always increasing, so always increasing, always positive, so it's always above the x-axis. And because it's always above the x-axis, that means like the amount of rice is always positive. You can't have a negative amount of rice. The asymptote is x equaling or y equaling 0. And then the end behavior as x increases, y increases, and as x decreases, y approaches 0. Next, the half-life of caffeine in the body of a healthy adult is approximately 5 hours. Suppose that an energy drink contains 160 milligrams of caffeine. The amount of caffeine Y left in your system after X 5-hour periods is modeled by the function Y equals 160 times half to the X power. Analyze the graph and graph the function, then find and interpret the key features, including any constraints on the domain in the context of the situation. So this one is graphed for us. Here you can see our graph. This is a decay. And how do we know that it's a decay? I go back here, I can see that my b is less than 1 but greater than 0, so it's an exponential decay. There you can see the table of values. They're using negative 1, 0, 1, 2, 3, and 4. See that it starts off with 320 and goes down to 10. So let's find and interpret the key features of this graph. So the intercepts only has the x-intercept, or the y-intercept, which would be 0 and then 160, which just means after drinking the energy drink, your body has 160 milligrams of caffeine. The domain here would be greater than or equal to 0. So the time period, amount of time, which is 5-hour periods, would just be x such that x is greater than or equal to 0. You can't have a negative amount of time periods, so it's always going to be positive. The range here, y such that y is going to be greater than or equal to, not greater, going to be greater than 0, but it never goes above 160. So the 160 is the highest it can go. And again, you're not going to have a negative amount of caffeine in your body, so that's why it stays above 0. Next, we got the asymptotes. The asymptote would be y equaling 0. So for that one, you're always going to have, you can't have the y value being 0, which means, or Yeah, it can't be 0 or below because that means your caffeine level is going to be 0 or below 0, and it can't get to that point. The end behavior be as time increases. I'm going to use an arrow. So as time increases, the amount of caffeine decreases. But it doesn't decrease indefinitely. It actually approaches. So I'm going to use approaches 0. Then increasing or decreasing, this is always decreasing, it's going down. And then it's going to always be positive, it's always going to be above the x-axis. But for the decreasing part, it's only decreasing until it hits 0, or gets close to 0. Our last example says, until 1972, a commonly used pesticide in the U.S. was DDT, which has a half-life of about 15 years. If a crop were sprayed with 200 grams of DDT, then the amount remaining Y after X cycles of 15 years can be described by the function Y equals 200 times half raised to the X power. Analyze the graph and the function, and graph the function, then find and interpret the key features, including any constraints on the domain in the context of the situation. Square B is less than 1 but greater than 0, so this is an exponential decay. Here we have a table of values. We're going to use -1, so -1 would give us 2 times 200 would give us 400. And then anything to the 0 power is 1 times 2 is 200, or times 200 would give us 200. Half of 200 would be 100. 200 divided by 4 would give us 50. So I'm really just taking half of each of these numbers. Half of 25 would be 12.5. So now in our graph, you can notice that I only have quadrant 1. And the reason why I'm using just quadrant 1 is because the domain has to be a positive number. So now if I plot these on here, I need to come up with my what I'm going to be counting by, so my y coordinates. So let's count them by, I'm going to count these by really 25s, but I'm just going to go up by 50s here. And that means each line is going up by extra 25s. So now if I plot these down, I'm not going to do the first one, -1, because that doesn't have any meaning to our problem. So I'm going to start with 0. And then down here, I'm just going to count these by 1. So 1, 2, 3, 4, 5. So plot them. I would have 0 and 200. So 0, 200 would be here. Then I would have 1 and 100. 2 and 50. 3 and 25. 4 and 12.5. So then if I were to draw my graph, it would come down something like this. And then we can do the key features here. So the intercepts on this one would be 0, 200. And what would that mean? Based on our problem, your y coordinates are the amount of DDT remaining, and x is the sickles. So you start off with start with 200, and then the label for this one would be grams. So it starts off with 200 grams of DDT. The domain here, the domain would be x such that x would have to be greater than or equal to 0, but less than or equal to, actually just that one would be just greater than or equal to 0. Our range here would be y such that y has to be greater than 0, but the maximum you can have is 200. As you can tell from our graph, it doesn't go above 200. Then our asymptotes be y equals 0, because the number of grams is always going to be a positive number. And so the end behavior, as the time increases, or the number of cycles increases, I'm going to use going up, the amount of DDT decreases, goes down, or not decreases, it approaches 0. And then this one would be decreasing, and it's always going to be a positive amount. So that is our lesson on interpreting graphs of exponential functions.